Okay, so here's some basic examples of finding related rate equations. First example deals with a particle moving along a curve. Right? So this particle is infinitely small and is traveling back and forth along some function of x with respect to y, or y with respect to x. Sorry. Okay. So if you think about this particle, it's a point on the line, and its slope is given by the slope of the tangent line, dy dx. But as this particle moves along the line, it's moving in the y direction as well as in the x direction. Right? These two directions, right, are called the components of the particle's change in position. Okay? So you guys taking physics, you know these guys as the the velocity in the y direction and the velocity in the x direction. But in calculus, we'll call this the change in the y coordinate with respect to time. How fast is the y coordinate changing? And then its distance or its velocity in the x direction is its rate of change of the x coordinate with respect to time. So it's moving, in this case, moving right and moving up. Okay. Question is, if you know one of these, can you get the other one? All right, so you say, well, if I have a function of x, which gives me the y coordinate, if I take its derivative with respect to time, I get dy dt, and then the derivative of the function x with respect to the variable t. So take a function like the square root of x. Put a particle on there and have that particle move in some direction. So in this case, we're said, okay, here's the path. We're told that's the path. And here is one of the rates of change. At any given time, the change in the x coordinate with respect to time is 3 units per second, which means it's moving 3 units to the right every second. And we want to find the rate of change of the y coordinate. Now we're going to end up needing some information besides its rate of change in the x direction. We're going to need to know where the particle is, because as this thing moves, okay, the change in the y coordinate may not be constant. Okay, so you start with the quantity, y equals x to the 1/2. That's y equals the square root of x. And you take the derivative of the quantity equation with respect to the variable time. And the y coordinate and the x coordinate are changing with respect to time, which in this case is in seconds. So the derivative of y is the rate of change of y. Right, this is a power. Bring down the exponent, leave the base alone, reduce the power by 1, then chain onto that the derivative of the base. But the derivative of x with respect to the variable t is dx dt. So there's your related rate equation. Just rearrange it, dy dt. Let's see, the 2 is in the denominator. Negative power becomes a positive power in the denominator, and the 1/2 power is the square root of x. There's 1 on top times dx dt. Now if you wanted to, you could make the numerator of this fraction, you could put dx dt up here, but this is easy to work with. All right, so there's our related rate. We want to find dy dt at this point. So dy dt equals 1/2 times the square root of x. Now x is where the particle is. So the x coordinate's 4, so I can put 4 into there, times the rate of change in the x coordinate, which is 3. Right, so dy dt equals 3 over 2 radical 4. We don't have a measurement for the distance, it's just units per second. Let's see, just for fun, alpha y equals 3, 2 times 2, which is 4. Okay. Square root of 4 is 2. That was a lot of work for 3/4. Should be able to do that in my head, right? 0.75 units per second. So as the particle moves right 3 units every second, it's moving up 3/4 of a unit every second.